All right, so here's what we had left in section 4.4. There are several theorems that are going to allow us different techniques for finding Laplace transforms and finding inverse Laplace transforms. And the first theorem is this. It's that if f of t is piecewise continuous and f of t is of exponential order, that's what that says, f of t is less than some exponential function, then the Laplace transform of negative t times f of t is the derivative of the Laplace transform of little f of t, or written as the derivative of big F of s. Equivalently, if f of t is the Laplace transform of big F, you can pull out this t, except we're doing inverse Laplace transform, so it comes out as a division, and you take the inverse Laplace transform of the derivative. And we'll see where those are used here in a few minutes. And a repeated application says, if instead of just having t, if I had t squared or t cubed or t to the fourth or whatever I had there, I could use this theorem over and over and over again, and I would end up with a negative 1 to the power, whatever my original power was, times the nth derivative of my Laplace transform. Questions on that? All right, so let's look at some examples here. Determine. I gotta. All right, so I want the Laplace transform of t times cosine of 3t. Here's the theorem that I'm using. If I have a t to the 1, this theorem says I pull out a negative 1 to the power, and then I take the derivative of whatever the Laplace transform is. So, to get rid of this t, I'm going to have a negative 1, and since this has power 1, this has power 1, times the derivative of the Laplace transform of cosine t. What's the Laplace transform of cosine 3t? S over s squared minus 3 squared. That was hyperbolic? Okay, then we'll do s squared plus 3 squared. That would be cosine. I was pointing to the wrong one. All right, so now all I have to do is take that derivative. What's that? Answer is negative 1 times. I take the derivative. I got to use the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. So my answer is negative 1 times. I have s squared minus 2s squared, so that's going to be minus s squared plus 9 over s squared plus 9 squared, which I would probably write as s squared minus 9 over s squared plus 9 squared. Take that negative 1 and multiply it through. Questions on that? Okay. How about the Laplace transform of, I don't know, anybody got a good function? T to what power? T to the fourth, e to the cosine t. Well, that would be a problem. The problem would be I don't know what the Laplace transform of e to the cosine t is. So how about we go e to the 2t? Thank you. You're welcome. All right, so according to this theorem that I'm using, if I have a t to the fourth, I'm going to have a negative 1 to the fourth. And then I need the fourth derivative. Why the fourth derivative? Because this theorem says if you have t to the power n, you have negative 1 to the n times the nth derivative. So since somebody foolishly picked t to the fourth, we're going to have to do 4 derivatives.
I thought that when you went for capital letter, that was usually with integrating. And when you went from capital letter to lowercase letter, that was
Quite often, yes. But in this case, we're doing Laplace transform. So notice we start with little f. When we take the Laplace transform of little f, we get big F. And you might remember that a Laplace transform is an integral.
Yeah.
So we are kind of keeping that same sort of notation. Okay. All right, well, what's the Laplace transform of e to the 2t? 1 over s minus 2. And then I have to take the fourth derivative of that. Well, the good news is the teacher was somewhat clever and picked e to the 2t, because I'm going to write this as s minus 2 to the negative 1. So when I take the first derivative, I get negative 1 times s minus 2 to the negative 2. And then I take the second derivative, I get 2 times s minus 2 to the negative 3. And I take the third derivative, negative 6, s minus 2 to the negative 4. And finally, the fourth derivative would be 24 s minus 2 to the negative 5. So taking the 4 derivatives there really wasn't that difficult. It would have been much, much more difficult if I had to put something like a cosine there. You can see how the first derivative came out. Now I'll imagine doing it 3 more times. That would not have been a good time. We wouldn't have finished today. All right, so final answer is 24 over s minus 2 to the 5th. Questions on that?
That's pretty straightforward.
Yeah, not so bad.
What happens if it doesn't have a T?
What happens if it doesn't have a t?
Yeah.
What would you like? I mean, if it just has a number in front of it, then we don't have an issue. The Laplace transform of 6 e to the 2t is just 6 times 1 over s minus 2. So if it's just a number out front, the number just stays. Not an issue. So maybe you're thinking, what if I had the Laplace transform of sine 3t e to the 2t? So we don't have just a t to a power here? Well, I look on my magic chart of Laplace transforms, and I happen to find one that has an e and a sine in it.
So
What if your magic chart doesn't have the right form in it? Then you're in trouble, probably. You're going to come up with something else. So the answer to this one would be, remember this one came from a couple sections ago. This was our translation theorem. When you have a function and you multiply it by e to a power, you get a shift of your original function. So that was our translation theorem. So this is going to be, what is it? 3 over s minus 2 squared plus 9. It's our traditional sine Laplace transform, shifted 2 units to the right. All right, how about,
what if we had like a T to the pi or something?
what if you had the t to a pi? Then you'd have an issue, because that theorem only works for integer exponents.
Okay.
Positive integer exponents. How about if I want the inverse Laplace transform of ln of s squared plus 1 over s squared plus 4. Well, there's something new. I don't think in any situation up to this point with Laplace transforms or inverse Laplace transforms have we seen an ln?
You should just not see that anymore.
Well, I can't just exponentiate it because, again, this thing involves integrals. Integrals don't work cleanly with just exponentiating. Well, here's what we're going to do. We're going to write this as the inverse Laplace transform of ln of s squared plus 1 minus ln of s squared plus 4. What have I done there? Just use a property of logarithm, right? The property of logarithm takes division, turns it into subtraction.
Maybe you can split the Laplace transform up.
I can absolutely split the Laplace transform up. That's true too. Doesn't really help though, because I still haven't gotten rid of those ln's, have I? All right. Well, here's what we're going to do. We had this theorem that said if we want the Laplace transform of t to a power times f of t, we're going to use it in reverse, which says if you want to do the inverse Laplace transform, instead of multiplying by a t, you divide by a t, and then you take the derivative of whatever you started with. So that's going to be very, very helpful. So this is negative 1 over t, the inverse Laplace transform of, I take the derivative. What's the derivative of ln of s squared plus 1? 2s over s squared plus 1. So that got rid of the ln, and it put us into a form that we recognize, don't we? At least I hope we recognize that at this point. Minus, this one's 2s over s squared plus 4. So that's what you do when you have ln's. To get rid of ln's, you use that theorem which allows you to take derivatives. And the derivatives of ln's gives you rational functions, and we know how to find inverse Laplace transforms of these things. Final answer, minus 1 over t times. What's the inverse Laplace transform of 2s over s squared plus 1? 2 cosine t. Minus, what's the inverse Laplace transform of 2s over s squared plus 4? 2 cosine 2t. Why 2t this time? Because of this k squared on bottom, because that 4 down on bottom, that's right. Questions on that? What it's going to come down to on the test is looking at a problem and being able to look at all the theorems and all the techniques you have and decide which one's the right one to use for this problem.
And you'll give us a practice quiz kind of thing, right?
And I'll give you a practice quiz kind of thing for you to do over the weekend. Absolutely. It's a lot like Calc 2, I agree. In Calc 2, there's a lot of pattern recognition. You had to be able to look at an integral and say, I should use integration by parts or partial fractions or whatever the technique. And then later on, you had to be able to look at a series and say, to show this series converges, I should use the ratio test. To show the next one converges, I use the alternating series test. I use the ratio test, the root test.
You brought up series, so I just need to double check. There will be no series in this course, right?
No, that's wrong.
There will be series?
For example, you might look at chapter 3, which is called Series Solutions to Differential Equations. So there will be series in this course, absolutely. Okay, the other theorem so we had this theorem which told us how to find Laplace transform if you're multiplying by a t. There's also another theorem which tells you how to find Laplace transform if you're dividing by a t. So the hypotheses are pretty much the same. It's piecewise continuous. It's of exponential order. There's one other little rule. No, I guess it's the same. But the Laplace transform, when you're dividing by a t, you integrate the Laplace transform of the original function. And conversely, you can find the inverse Laplace transform of something by multiplying by a t and then doing the inverse Laplace transform of the integral. Okay, so these sort of problems going to look like this. Find the Laplace transform of 1 minus cosine 2t all over t. Well, our theorem says we can get rid of that dividing by t if we're willing to integrate from s to infinity. We get rid of the t and we find the inverse Laplace transform of 1. I'm sorry, the regular Laplace transform. I'm doing Laplace, not inverse. We'll see Laplace transform of 1. Except I don't want to use s because I'm using s here. So you might notice in the theorem in the book they used some Greek letter for some reason. I think I'd rather use an x.
Yeah.
Minus. What's the Laplace transform of cosine 2t? X over x squared plus 4 dx. All right, so you get rid of the t, you find the regular Laplace transforms, and then you have to integrate. What's the integral of 1 over x? ln x. Minus, what's the integral of x over x squared plus 4? It's a u sub. U is x squared plus 4, so du is 2x dx. So I need a 2 there and a 1/2. I'm going to end up with 1/2 ln x squared plus 4. Absolute values, true. I don't really need absolute values though because we're only using positive numbers. So from s to infinity. All right, so what happens when x goes to infinity? When x goes to infinity, what does ln x do? It gets really big. That one goes to infinity. What does 1/2 ln of x squared plus 4 do? What's infinity minus infinity? Sometimes it's 0. Sometimes it's infinity. Sometimes it's negative infinity. Sometimes it's any number in between. Which one is it for this problem? Negative infinity. Nope. 0. Yes. Why? Because that makes it nice. Oh, well, we like it when it's nice.
There's 3 options and somebody that picked one.
No, there was an infinite number of options. I said it could be any number in between. I'm going to rewrite this as ln x divided by x squared plus 4 to the 1/2. So again, I'm using my properties of exponents. This 1/2 goes in, it becomes a power. Logarithms take subtraction, turn it into division. Now what happens when x goes to infinity? Now I'm in the form infinity over infinity. I don't think so. Because I have an x squared, but I also have a square root. So in essence, the top and the bottom have exactly the same power. So when x goes to infinity, this all goes to 1, and the ln of 1 happens to be 0. Minus, I got to plug the s in, so I get minus ln of s over s squared plus 4 to the 1/2.
That's crazy.
Questions on that one?
So wait, how are we going to go from ln? How are we going to go from that to that?
From here to there?
No.
From there to there?
Yeah.
when x goes to infinity, this is in the form infinity over infinity. But if you check your powers, you have power 1 on top, and here you have an x squared, but you also have a square root, so you have power 1 on bottom also. Since the power on top and bottom are the same, you look at the leading coefficients, which is 1 over 1, which is 1. And so, that's the limit. That's right. So the limit here is 1, and ln of 1 happens to be the number 0.
So it's... But I thought the Laplace transform 0 is... Oh, so you just replaced the x's here.
I'm taking... So I'm doing two things. I'm taking the limit as x goes to infinity. When I take the limit as x goes to infinity, that's where I got the 0. And then minus, and I plug in the s.
Oh, I see. Okay.
And there's what I got. All right, so the last thing in this section. We have finally reached one of our ultimate goals of Laplace transforms. Other than being done with them. What were our big goals with Laplace transforms? Solving differential equations that we could not solve with what we learned in Chapter 2. And one of the big things we could not do in Chapter 2 is have variables out here as our coefficients. That was one of the goals of Laplace transform. The other goal of Laplace transform we'll do tomorrow. The other goal was to be able to solve non-homogeneous equations where this thing over here was a discontinuous function. So those were really our two goals. Those were the things we could not do in Chapter 2. Oh, we need an initial condition here. How about x at 0 equals 0? Okay, so going back through what we know. What's the Laplace transform of the second derivative? S squared big X minus S x at 0 minus x prime at 0. Well, kind of broke there. This one is 0, so that one goes away. But we really need the Laplace transform of t times the second derivative. What does multiplying by that t force me to have to do? Not integrate. When I divide by t, I integrate. When I multiply by t, I take the derivative. That was our theorem right here that we just had. When I have t to the 1, I multiply by a negative 1, and I take the first derivative. All right. So this is going to be negative 1 times, what's the derivative of s squared times capital X? 2s capital X plus s squared x prime at s. Where did the 2 come from? The 2 came from the derivative of s squared. The derivative of s squared is 2s. So, notice we have multiplication there. This one has an s in it, and this one also has an s in it. So I have to use the product rule. So I took the derivative of the first one, that was 2s. I left the second one alone. Plus, I left the first one alone, that was s squared. I have to take the derivative of the second one, that's x prime. We're taking d ds, correct, d ds. X is not a constant though. X is a function involving the letter s. X is not a constant. So that's why I had to use the product rule there. Now, this x prime at 0, notice they didn't give us an initial condition for x prime, but what's x prime at 0? That's a constant, so when I take its derivative, it is 0. So So there's the Laplace transform of t times the second derivative.
Oh, that's it?
Well, that's it for that. Now we keep going. Notice that we have a t times our first derivative. So we're going to have to go through the same process for that. We remind ourselves that the Laplace transform of the first derivative is s times capital X minus x at 0. But once again, x at 0 is 0. So when I go to do the Laplace transform of t times x prime, I've got to do the same thing. It's going to be negative 1 times the derivative of s times x of s.
You don't need the t minus 2.
I'll need the minus 2 also. So what I'm thinking is I'm thinking of this as tx prime minus 2x prime. So I'll deal with the tx prime and I'll write that down, and then later on when I go to write the whole equation I'll put the 2x prime down. Okay, so I take the derivative. I take the derivative of the first one, that's 1. I leave the capital X alone. Plus I leave the little s alone, and I take the derivative of the capital S. Okay, so now I'm ready to take my original equation and transform everything using Laplace transforms. I'm going to take this negative sign and distribute it through. Negative 2s capital X minus s squared capital X prime. And then I have the t times x prime. There's my t times x prime. So that's negative capital X minus s capital X prime. Then I need 2 times my x prime. So that's minus 2s capital X. Plus the Laplace transform of little x is capital X equals 0.
Big X and big X primes.
Yeah, we do. Seems like something's missing now. Where'd the what come from?
Oh,
That's an S.
Is that supposed to be a t plus 2?
Plus 2.
Up at top, at the very beginning. Is that supposed to be a plus? Is that minus?
That's a minus. I copied that right out of the book. All right, we're okay. You may ask a question.
Which part of that came from the minus 2x?
Okay, so this part, this came from the tx double prime. This part is the tx prime. This was the minus 2x prime, and that was the x. Okay, so here's what we're going to do. We're going to get all the things that have the capital X prime on one side and all the things that have just the x on the other side. That means I have minus s squared x prime minus s x prime equals there's a lot of them here. I got to cross them. So I use that one and I use that one. What do I have here? I have minus 4. So when I move it to the other side, it becomes a plus 4 x of s. And then these two reduce each other out, don't they? Why did I want to get all the x primes on one side and all the x's on the other? It allows me to factor out the x prime, or over here, if I had a bunch of x's, I could factor those out too. I factor out the x prime. X prime of s is, oops, times minus s squared minus s equals 4s capital X. Alright, then I'm going to write this as x prime of s over x of s equals 4s over minus s squared minus s. What did I just do? Well, I divided by the x of s and I divided by the minus s squared minus s. But why is that important? What's that?
ABX kind of deal.
No, not quite.
It's because you're in a separation where you take the derivative or something.
I'm going to do what Greg just said. What'd you say?
Separation of variables.
Separated my variables. Notice that I have all the x's on the left-hand side, and I have all the s's on the right-hand side. We have a separable differential equation. Way back to chapter 1. All right, well, let's clean up this side over here a little bit. I'm going to write this as minus 4s over s squared plus s. I multiplied top and bottom by negative 1. And then notice I can factor an s out of the bottom. So that's negative 4 over s plus 1. The key is I now have a separable differential equation, which means I ought to be able to integrate both sides. What do you get when you integrate x prime over x? I don't get big X. You get ln of big X. Absolutely. Think about if we had the integral of 1 over t dt. We have t on bottom, the derivative of t is 1, we would have ln t. We have a function on bottom, its derivative on top. That's a u sub. If I let u be the bottom, its derivative would give me the top, so I would have 1 over u du. So that's ln of big X. Which seems a little scary until you come over here and you integrate this one. What's the integral of negative 4 over s plus 1? Negative 4 ln of s plus 1 plus c. You get rid of your ln's. You have x of s is, what happens when you exponentiate the right hand side? This negative 4 is going to come in as a power, and then what happens when you do the e? You multiply by c, so you're going to have c over s plus 1 to the 4th. And finally, little x is, you look on your big chart of Laplace transforms, you're looking with something that has s plus 1 to the 4th down on bottom. How about s plus 1 to the 4th down on bottom? If I have an s plus 1 to the 4th down on bottom, what do I need up on top, though? I need a 3 factorial, which is a 6. So I need a 6 on top, which means I need a 1/6 there. So that's going to be 1/6 times c, and this is going to be e to the at. A is, in this case, negative 1, so that's going to be e to the negative t times t cubed. There's the answer. Questions?